On a number of the previous videos, we looked at various AC electrical circuits with capacitors, inductors, transformers, and so forth. And it has occurred to me that a lot of people don't really know how to handle AC circuits in terms of Ohm's law. In high school and probably first year university, many of you would have seen how to handle a simple DC circuit with Ohm's law, how to calculate currents from voltages and resistances. Well, it turns out we can do the same sort of thing with alternating current circuits. And it's really not that hard. In fact, it's not much different at all. So this video is what that's all about. And, well, let's get started. So let's start with a very simple DC example, and then we'll work our way down to more and more complicated AC examples. And the circuit we're going to use for our example is a nice simple battery that we'll draw like this. And we'll put a plus and minus on it. And the very complicated circuit that it's attached to is a resistor. We'll call the resistor R. We'll say that there is a current I flowing through the circuit, and the voltage of the battery is V. And what we'll do is say V equals 120 volts DC, R equals 10 ohms, and if we use the standard Ohm's law equation, which is I equals V over R, well, if we take V, we divide it by R, well, 120 divided by 10, so current equals 12 amps, and we'll just write DC to remind ourselves that it's DC. And that should be of little surprise to anyone, I hope. Now, let's do exactly the same thing with a very simple AC circuit. Well, we're going to start off with an AC source instead of a battery, which we'll draw like that. And once again, we will include our very complicated circuit like this. And once again, this is the resistor R. There is a current I flowing through everything. Oh, and we better keep track of polarity. So there's our plus and minus again. And here is our voltage V. So really, it's almost the same circuit. All right, so let's fill in some of the values. So V this time is AC. So we're going to say V equals 120 with a phase angle of 0 degrees. And that would be, if you want AC volts. All right. I've used this notation before, and it's a way of combining the voltage of the AC signal with the phase. In other words, how much our sine wave has shifted. And a shift of one cycle is 360 degrees. A shift of half is 180 degrees. A shift of a quarter is 90 degrees, and so forth. And we have a name for this notation, and it's called a phasor. And no, it's not that type of phasor. In fact, electrical engineers have been using phasors way before Starfleet ever used them. Anyway, that's the phasor representing the voltage, and the resistance is still 10 ohms. We want to keep things as simple as possible. And now we need the current, I, and I equals 120 angle 0 degrees divided by 10 ohms. We could even extend the 10 ohms to become an impedance that may have an angle of itself. Well, a pure resistance has no angle, so it's 0 degrees. And it turns out that if we do the division here, we end up with, surprise, surprise, 12 amps, and that 12 also has an angle, and it has an angle of 0 degrees. And so it's basically 12 amps AC, like that. Now, just for now, bear with me that if you take something with an angle divided by something else of the same angle, you get 0. In fact, what's happening is when you do a division with phasors, the numbers here divide and the angles subtract. All right, so that was really just the same thing between AC and DC, and if we decided to eliminate the fact that we had phasors, well, that would just simply be 12 amps, and that would work out just fine. Okay, now for the fun part. We will repeat the example. We're going to have a nice little voltage source, again like that. V volts. We will have a current I, but instead of a nice simple resistor, we'll put in an inductor, like that. And we'll call that inductor L. That's what we usually name inductors for some reason. And once again, just like down here, we'll say the voltage is 120 volts at an angle of 0 degrees. AC volts, just to remind ourselves. And the reactance, instead of resistance, we'll use R. They both start with R, so that's fine. Is, well, what is the reactance for an inductor? And the reactance is 2 pi. Pi is 3.14159 going on to infinity, times the frequency of the AC, times the inductance of that coil, times, well, not times, with an angle of, wait for it, 90 degrees. Okay, so all we have to do now is know what L is, the inductance of the coil, and then we can calculate what R is. Well, what I'm going to do is say, well, we're in Canada, so this is 60 hertz, and the inductance, I'm going to say L is 0.026 henries. So that's all times 0.026 at an angle of 90 degrees. And if you do this multiplication over here, what do you get? You get approximately 10. I chose that at an angle of 90 degrees. So there's our reactance right there. Well, we now do I equals V over R equals 120 at an angle of 0 degrees divided by 10 at an angle of 90 degrees. And the rule is we take 120 and we divide it by 10, and so we get 12. And for phasors, when we do a division, we subtract, so 0 minus 90 is, well, negative 90. So here we go. And that is our current. And so what does that say? Well, we had a reactance of 10, just like we had a resistance of 10, So we ended up with 12 amps. Because we had a phase angle in the reactance, we ended up with a phase angle in the current. And if you remember from previous videos, inductors causes the current to lag the voltage, and that's because the inductor's doing everything in its power to try and stop a change in voltage, so it slows down the change, and it turns out that results in a 90-degree lag in the current. Well, 12 amps at minus 90, minus 90 says the current is lagging. That's what the minus says, and the 90 is 90 degrees. That's exactly what we would expect for a decent inductor. Now, I'm going to repeat this one more time for a capacitor. And if this is completely obvious to you, you may wish to skip it, or you may wish to work through that with me again. All right, so once again, we will start with our nice little voltage source called V, and we'll draw a couple of wires, and this time we will connect it to a capacitor C. And like before, we're going to have a current I flowing through everything. And once again, we will say V equals 120 volts at an angle of 0 degrees, volts AC. Now, you might ask, what is the reactance for the capacitor? Well, the reactance of a capacitor is equal to 1 over 2 pi times the frequency of the AC waveform times the capacitance, and all of that has an angle of minus 90 degrees. And we're going to say C equals 265 microfarads. Capacitors are often in micro or nano or picofarads. It just turns out that those sizes are the most typical sizes of capacitors we deal with. You used to never be able to get capacitors of a value of a farad or more, although now with supercapacitors you can actually do it. But one rarely sees them except for power storage applications. All right, so let's see if we can figure out what the reactance of our capacitor is. Well, it's 1 over 2 pi times 60 because we're in Canada, times 265 microfarads, that's 0.000265, and all of that at an angle of minus 90 degrees. And if we do the calculation, we find out that this number is, surprise, surprise, 10. And so it's 10 at an angle of minus 90 degrees. Okay. Well, once again, we'll use the nice old Ohm's law of I equals V over R. And in this case, R is the reactance of the capacitor, so we'll just put a C in there. And so what we'll say is I equals 120 volts at 0 degrees divided by 10 at an angle of minus 90 degrees. And the rule again is for division, we divide the magnitude of the phasor, so we end up with 12, and we subtract the angle, so 0 minus 90 produces an angle of 90 degrees, so the current is 12 amps AC at an angle of 90 degrees. What does an angle of 90 degrees mean? It means the current is 90 degrees ahead of the voltage. It precedes the voltage. And indeed, that's what we saw in the previous videos. So this very nicely describes what's happening. Okay, well, that's very nice, but really a circuit like this or any of the other ones we've looked at is so simple, it's almost useless other than for a simple example. Okay, so now maybe we'll try a slightly more challenging example. And once again, we'll start off with a voltage source, V, and that voltage source is going to go to an inductor, and it's going to go through a resistor, and it's going to have a current I, just as we did before. This is the inductor L, this is the resistor R, and what we'll do is we will assume that this was the inductor we used in the previous example, this was the resistor in the previous example. So what we can do is write down for the resistor, well, its resistance R equals 10 ohms. And similarly, the inductor in our example, we decided its reactance is 10 at an angle of 90 degrees. All right, so what's the rule when we have a couple of resistances in series for DC? We add them. Well, it turns out we can do exactly the same thing here. And the total resistance, the total impedance, I should now say, is simply the sum of these two things. How do we add them? We'll look at that a bit later. So once again, we have the very simple Ohm's law equation. In this case, I equals V over the total of all of this. So we'll just say it is L plus R. And if we fill in some numbers, we get 120 volts at an angle of 0 degrees. And what we'll also do is now put in L, which is 10 at an angle. That should be 90 degrees. 10 at an angle of 90 degrees. And we will add to it 10 ohms. And ohms has no angle, so we'll just say it has an angle of 0 degrees. And you say, how on earth is he going to add these two things together and then do this division? Well, I'll show you how to do this later, but a far easier way is to use an online calculator. And you'll see a link. The first thing we do is we have 120 at an angle of 0 degrees, so we're going to enter that, and I'm going to put that whole thing in brackets just so we make sure we get the order of operations right. So there's 120 at an angle of 0, and just a note here, the angle has to be within brackets itself in this calculator. If you don't have these brackets there, it doesn't work, as I found out a while ago. So anyway, we're going to take that and we're going to divide it by, and I'm going to put in another pair of brackets just to make sure we are dividing by everything over here. And the first number we have is 10 at an angle of 90. And one thing I should point out is we have to make sure degrees is selected for all of this. The system defaults to radians. We're going to use degrees. And just so you know, there are 2 pi radians in a circle. There are 360 degrees in a circle. And they are really equivalent, but it's easier to think of as degrees for these purposes. Anyway, there's our 10 angle 90, and we're going to subtract 10 angle 0. And that should be all we need. So we get 8.5 at an angle of minus 45 degrees. And does that make sense? Well, if we had a purely resistive load, we would have an angle of nothing. If we had a purely inductive load, we would have a 90-degree delay, a delay shown as a phase of minus 90. Well, we would expect something in between. Well, minus 45 is exactly in between. That also makes sense because both these currents are of the same magnitude. So indeed, a current of 8.5 amps at an angle of 45 degrees makes perfect sense. Now, there are a few things we can look at when we look at this current. Well, if these were resistors here and they were each 10 ohms, we would expect at 20 ohms here to have half the current. Well, we have more current than we would expect if these were both resistors. Why is that? Well, it's because the voltages across these two things, which are at phase angles to each other, don't add up as the simple sum of the two voltages. They actually end up being as if they were sides of a right triangle, with the sum being the hypotenuse. And if you remember the Pythagorean theorem, you can figure out how big that is, and it turns out it's that big. All right, that was very nice, but now let's look at a really interesting example that shows how mind-boggling these types of circuits can be. Okay, here is one of the coolest simple circuits you will ever see. And it's something like this. Again, our nice little AC voltage source over here. And what we'll do is have an inductor, L, a capacitor, C, and, surprise, surprise, a resistor, R. And once again, what we're going to do is use all the same values we had before. So V equals 120 at an angle of 0 degrees. R is equal to 10 ohms. And in Phasor notation, we can write that as 10 of an angle of 0 degrees. The capacitor over here is equal to, what is it equal to? It's equal to 10 at an angle of minus 90 degrees. And the inductor over here is equal to 10 at an angle of plus 90 degrees. There we go. And once again, we can just use the standard Ohm's law equation, I equals V over R, where in this case R is the sum, because these things are in series, so it's the sum of these three things. And R is no longer resistance. When we have these phase angle type things in there, it's now called impedance. So we can start filling in the values. There's 120 at an angle of 0 degrees. All divided by, what's the mess we're going to put down here? It's going to be horrible. Well, let's start off with 10 at an angle of plus 90 plus 10 at an angle of minus 90 plus 10. Now, here's the really cool thing. Sure, these phasors represent the reactances of these two components up here. But remember, these phasors have an angle that represents a position on a waveform. And if we have a waveform like this, a nice sinusoidal waveform, we'll draw it as a sine wave. There we go. If you recall, that's sort of the 90-degree point. Well, if you have one point that, well, okay, I'm going to just draw it negative like that too. So here is plus 90, here is minus 90. So plus 90 is at a 1, minus 90 is at minus 1. Well, the answer is these two numbers are equal and opposite. And you know what that means? They cancel out completely. And so we end up with 120 at an angle of 0 degrees volts over 10 ohms equals 12 amps at an angle of 0 degrees. Do you believe me? We've got an inductor, we have a capacitor, we have a resistor. We just worked through the calculation, and it said these two things have no effect whatsoever. Now, even more mind-boggling, what we can do is we can figure out the voltage across each of these components. And if I equals V over R, well, V equals I times R. I've just rearranged the things in this equation over here. Well, I over here, we know, is 12 amps at an angle of 0. So 12 amps at an angle of 0 times R, which is 10 ohms. What does that give us across the resistor, the voltage across the resistor over here? Well, that gives us 120 volts at an angle of 0 degrees, which you might recall is the voltage over here. All right. What do we have across the capacitor? Well, V equals I, so 12 at an angle of 0 degrees, times the reactance of the capacitor. So it's times 10 at an angle of minus 90 degrees. And you put all of that together, what do you get? You get 120 at an angle of minus 90 degrees. The rule is, for multiplication, we multiply the magnitudes and we add the angles. So the voltage, maybe the VR for there, V across the capacitor, is 120 at an angle of minus 90. That's a bit hard to see. That's a minus 90. Unfortunately, you'll have to imagine it. So what does that mean? What does minus 90 degrees for the voltage mean? Well, the current we know is at an angle of 0 degrees. If the voltage is minus 90, it means the voltage lags the current by 90 degrees. If the voltage lags the current by 90 degrees, it means the current precedes the voltage by 90 degrees, and that's what we know happens in capacitors. So that is correct. All right. So now what about the voltage across the inductor? Well, it's really the same calculation here, except instead of a minus, it's a plus. So we end up with 120 volts at plus 90 degrees. So we now have 120 volts here at 0 degrees. We have 120 volts here at minus 90 degrees. And we have 120 volts up here at plus 90 degrees. That seems crazy. Each one of these things has 120 volts across it, and they all add together to become 120 degrees. Well, why is that? Well, the phase of this voltage is minus 90. The phase of this voltage is plus 90. That means the difference in phase is 180 degrees. Well, 180 degrees is exactly half a cycle. That means the voltages are equal and opposite. That means this voltage adds to this voltage to create 0 volts together. And so there is no voltage across the combination of these two components, even though there is a voltage across each one of them. So there's really 0 volts across here if there's no nonlinearities or non-ideal behavior of these components. There is no voltage across here. That means the full voltage from the source is across this resistor. It's like these two things never happened at all. Now that might seem very weird, but more than likely you've used circuits like this many thousands of times during the course of your lifetime. And they are what we call tuned circuits, because this situation where this impedance is equal and opposite to that impedance only occurs at one particular frequency. And by changing the size of the inductance or the size of the capacitance, we can change the frequency at which point they're equal and opposite. When they're not equal and opposite, you start having a voltage drop across these two components, and so you get less voltage across the resistor. Well, that's how we tune radio circuits. We adjust the L and the C so that at the frequency of the radio station that we're interested in listening to, these two things cancel out, and you get the entire signal coming from the antenna going to the amplifier over here. And for the radio stations at all the other frequencies, well, suddenly the L plus C no longer cancel out, and so they start using up more and more of the voltage from the antenna, and the amplifier gets less and less. So that's a very simple tuned circuit. It is really a mind-boggling type thought that you have three things with equal voltages across them, and yet the total is simply the voltage across this resistor. So you might have to think about that a bit. It is a little bit mind-boggling. It is, in my mind, one of the most interesting examples of a circuit that has both inductance, capacitance, and resistance. Okay, you didn't expect me to show you a circuit where there was an inductor, capacitor, and resistor, and when you measured the voltages across each of them, you would get a result, if you summed them, to be way more than the voltage of the input supply without doing a demo. And here's the demo. So I have a AC voltage supply here, well, attached to this quick test, and the line voltage goes into here. Here is going to be our inductor. It's a transformer core. It has some secondary windings that are just sitting here, not attached to anything. It has a pair of primary windings. I've put them in series. If it was a transformer, it would be a 240 volt transformer that way. And by the way, these are the same cores that I used in the electromagnetic chains video. And anyway, the other end of the primary gets attached to this bank of 5 capacitors. The capacitors are rated at 0.01 microfarads each, so we have 0.05 microfarads in total. And then from here, we go through this ammeter so we can look at the current, and then the ammeter goes back to the quick test to complete the circuit. And we also have everything coming through our nice little power meter, mainly so that we can watch the voltage on it as well. And oh yes, I have this voltmeter over here that we'll use to measure the voltage across the inductor and capacitor. So the first thing I'm going to do is turn on the power here. I've got this connected to a variac. I'm going to bring the voltage up to about 60 volts. There's no reason to go higher. And 60 is a nice, easy number to compare things with. So there we go. 60 volts or so. Close enough. All right. 60 volts. Well, let's maybe just confirm that this voltage is consistent with that voltage. There we go, 60.2, that's 59.9, good enough. And let's look at the voltage across our capacitors. 68 volts, so the voltage across the capacitors is already 8 volts larger than the input voltage. Let's look at the voltage across the inductor. 62, so it's a couple of volts more than the input voltage. And just one more time to confirm, the input voltage across the inductor and capacitor is only 60 volts. There, almost exactly. So that's really quite remarkable. Each one of these two components has more voltage across it than the total input voltage. So there you go. Why didn't I add in a resistor? Well, there are enough core losses in the core of this transformer, this inductor, to limit the current somewhat. So we really didn't need to add in a resistor, and adding in a resistor would just make the result a bit less spectacular. So there you go. There is an example of exactly the stuff we looked at in the example calculations. And since the current is 1.3 milliamps and we know all the voltages, the total across the system, across the inductor, and across the capacitors, you could now, using phasors, calculate what the phase angles of the individual voltages across the capacitor and inductor actually are. So there you go, a real-world example of what we talked about. Okay, so I promised you I would show you in a little bit more detail how those phasors multiply and divide and add and subtract. And to do that, we're going to draw them on a graph like this. And what we're going to do is use this axis on the graph to represent 0 degrees in our phasor, and this axis over here represents 90. This axis represents 180. Going in the other direction, this is minus 90, and of course, since there are 360 degrees in a circle, you can sort of work your way around this way and get 180 and minus 270 and all the way around to minus 365, which is the same as 0. Or you can work your way around here, get to 180, 270, and again to a full 365, which is again 0. So if you do a calculation and you find you have some number like, I don't know what, 359, well, you know, it's really the same as minus 1 degree. Anyway, that's how we represent angles. And just to sort of put things on perspective, here is our nice little cosine wave that looks something like that. And going from here to here, from this point to this point, in other words, the identical point one cycle on, that's 360 degrees, just as a reminder. And if we go half a cycle from here to here, that's 180 degrees, and when you're half a cycle, you're always 180 degrees out. You're always equal and opposite. So here to here is equal and opposite. If we moved over a bit, here to here is equal and opposite. Okay. The easiest way to see how things work is we'll use some examples and some of the numbers we've used before. And maybe we'll start off with a voltage of 120 volts at an angle of 0 degrees. And maybe what we'll do is we'll represent it along here. So we would count along 120 notches along here. And we'll say that's over here. It's 0 degrees, so it's on the 0 degree axis. And what we conventionally do is draw it like this with an arrow. All right, now let's imagine we had a current of I equals 12 amps, which is what we were using before, at an angle of 90 degrees. Well, 12 is sort of a bad number for this because it's so much less than that, so 12 would be somewhere around here. The angle is 90 degrees, like that. and we would draw that 12 at an angle of 90 as a very short arrow pointing up along the axis. Well, that's easy enough. Now, we had dealt with another number in one of our examples, and it was a current of 8.5 at 45 degrees. Well, we'll pretend it was a voltage. And I'm just thinking here, this should be in purple. We'll pretend it was a voltage, so we'll say there's another voltage. We'll call it V2. And what we will say is it is 100, just so it's similar size arrow, at an angle of 45 degrees. Well, 45 is somewhere along here. If we were to say this, that is 120 here, so 100 is maybe something like that. So this is how we would draw our V2, where this angle is 45. Okay, so the first thing is, how do we multiply or divide these things? Well, I told you those rules before, but we should just write them down. So multiply, we take the magnitude, the voltage or the amps or the ohms or whatever it might be. So the magnitude times the magnitude. And what do we do with the angles? We add the angles. Divide, which is really the opposite operation of multiplication, is, well, we divide the magnitudes, just as if there was no angle at all, and then we subtract the angles. Now, in terms of why that is, I think the best point right now is just to accept that there's a fair amount of math behind it that we really don't want to get into. All right, the unfortunate thing is, if we want to add things or subtract things, it's a little bit harder in this phasor format because we can't easily add them. So what we have to do is add them graphically. So if we wanted to take this voltage and add it to this voltage, we would take this arrow and leave it where it is, and we would take this arrow and line it up so that its end is where so that where its start is where this arrow ends. So if we take this arrow and move it over here, I'm just going to draw a dotted line to give us the height. The angle is something like that. So here we go. This is really V2 now. We line them up like that, and I'm going to reuse blue. The sum of these two is that. So if we had some good graph paper, what we could do is we could measure how long this arrow is and see how many volts it actually is. And we could maybe use a protractor and we could look and see what its angle is. And that would give us the phasor, the voltage and angle of the sum of these two phasors over here. And if we were going to do subtraction, well, we just reverse the direction of the arrow we're subtracting. So if we want to subtract V2 from V1, what we'll do is we'll take V2 and we'll reverse it. So now its arrow is on the other end. And once again, we'll draw something like that. Like that. And then our result will be, and once again we could use a protractor to measure the angle here, and use a ruler to measure the distance, and that would give us the subtraction of the two phasors. And that nice little online calculator does exactly that. Now, what I didn't tell you, but if you've had some complex math before, what you might realize is this is really a very quick introduction to complex numbers, where this is the real part and this is the imaginary part of the number, where the imaginary number is equal to the square root of -1, but that doesn't really come into play in anything we're doing. We can just accept that. And as I mentioned in the previous video, there is a perfect mapping between all the stuff we need to do with AC current calculations and complex numbers. And indeed, when we used phasors to calculate power, where power equals volts times amps, well, if volts and amps are phasors, you get a power that is a phasor and may have some angle to it. And if we were to plot that power on the graph paper, and let's pretend that this blue line is the result of a multiplication like that, well, we can take that blue line and bring it down over here to the real axis, and that point on the real axis, in other words, this length here, is the real power, the actual power that's being delivered to the load. And quite similarly, we can take a line over here to this imaginary axis, and this distance over here is the amount of reactive power, the power that's going back and forth in the power line, but not delivering any real power to the actual load. So the imaginary axis, an imaginary number, corresponds to reactive power. The real axis, or the real part of the phasor, corresponds to real power. Isn't that cool? Well, I think that's enough of that right now. If you have any questions, be sure to ask them in the comments, because I can certainly see this was a very fast crash course. And even if you find this kind of mind-boggling, the fact is you can use something like that online calculator to do the calculation without having to worry about all the theory between how you add and subtract or multiply and divide phasors. And if you do have a scientific calculator, many of them do handle complex numbers and have built-in functions to go from this format to a Cartesian type format that has the real part and the imaginary part of the phasor, as opposed to the magnitude and the angle, and you can just flip back and forth between the two types of representations, and you can multiply and divide and add and subtract without even thinking about it. So the online calculator was just a way that I could show you how to do it, and if you didn't have a fancy calculator, you can certainly use that very nicely. So that's how to calculate currents in an AC circuit, and I think you'll agree, I hope you'll agree, that it's really not much different than calculating currents in a DC circuit. And the main thing really is instead of resistance, we're using impedance, and we're also carrying the phase through all the calculations. If you have any questions or thoughts, please feel free to put them in the comments below. And if you do have any questions that you'd like me to address in future videos, send me an email, or again, ask them in the comments. And if you did like these series of videos or any of the other videos I've done, please consider subscribing. It's really helpful for a small channel like this one. And, well, see you next time.